Good afternoon, everyone. Welcome to this afternoon's scikit-image tutorial. Thank you for being here. While I'm giving the introduction to the tutorial, I would like you to make sure that you've got the lecture materials on hand. You can find that at the URL indicated. So please clone that GitHub repository. If you aren't familiar with Git, you can also go to that page on GitHub and click the download button. You should be able to get a zip download that you can extract. I updated the material fairly recently, so if you could just refresh your repositories, that'd be great. Thank you. The tutorial this afternoon will be presented by myself, by Claire McQuinn in the back, and by Emmanuelle, who's a core contributor to scikit-image. Come on in. So scikit-image was founded around 2009 as a collection of image processing scripts for use inside of the SciPy ecosystem. Scikit-image itself built on top of existing tools like NumPy and SciPy. Specifically, we make use of SciPy's indie image submodule, which contains a lot of the underlying low-level functionality that we employ for image transformations, interpolation, and that sort of thing. So whereas ND image is fairly low level, scikit-image aims to provide a Pythonic high-level interface to provide the basic building blocks for doing advanced science, and to make it easy to use all of these components together so that you can easily get started doing your experiments. So today we're going to cover somewhat different parts of the library than what we've covered in previous tutorials. How many of you have been at one of these before? Okay, great. So we'll start with a short introduction, because I know some of you just finished the software carpentry lessons. So I want to make sure that that you're all on board. So I'm going to discuss with you briefly how do we represent images in scikit-image by using NumPy arrays. And I'll give you a few examples of that. Then we're going to move on to a topic that's now become very popular, which is the processing of three-dimensional data, which Claire will talk about. And then Emmanuelle will discuss machine learning applications in image processing. And then to round off, I will give you a bit of an overview of some other libraries that you can interact with scikit-image. All right, so I think you all got the installation instructions beforehand, so I hope you have working versions of scikit-image installed. A quick check you can do is to do, well, you should make sure you've got NumPy. So you should have version 1.13.1. 1.13.0 might give you some problems because of a bug that they fixed recently, or a deprecation that they de-deprecated. Larger. Yeah. There we go. So if you're running pip, you can pip install any of the packages that you're missing. If you're running conda, use conda install with a package name, and you should get the latest package version. With regard to scikit-image, you should have version 0.13. That's the latest release. All right. Can I just have an indication who does not have the correct version of scikit-image installed in their machine right now? Okay, so 12. You've got 12? Okay, so Claire will give you a hand. Right, so I've given you a brief overview of how this tutorial is going to be structured. Just a note for your own benefit, the snacks outside are available until 4 o'clock, and coffee will be removed at 5. So feel free to leave during the exercises to go and rehydrate. The lecture materials that you just cloned, there's a massive amount of material available there. We're only going to be able to scratch the surface of that, but you should feel free to explore the repository. I've given you the link there to the lectures themselves. They're all in the lectures directory that we're going to be using today. And then I also added some Stack Overflow challenges in there in case you feel like testing yourself a little bit afterwards. So scikit-image was born out of a real-world need to do science, and I'd like to give you a few examples of places in which it's been used. If you're interested in further reading, we've got a paper out on the library itself that's published in PeerJ, and then recently Emmanuelle and I and Juan also co-wrote a paper about the use of scikit-image in X-ray imaging. Like I mentioned, scikit-image is part of a much larger ecosystem of packages. And one of the wonderful things about the scientific Python ecosystem is that all these packages speak to one another, mainly through the common exchange interface that's known as the NumPy array. So you can use scikit-image together with scikit-learn. You can use it with pandas and matplotlib, all the different libraries that you've heard of before. We'll see various examples of its use today. Here's just a short excerpt of filtering, feature extraction, segmentation, and making measurements on objects. If you want to have a better overview of all the functionality available, please go to the website. We've got a gallery of examples that highlights almost all of the functionality inside of scikit-image. One of our recently joined core team members, Alex, submitted this example. He uses scikit-image to work on radiometric dating of materials. Emmanuelle works in materials sciences, so she sent me these beautiful pictures. The GammaPy project uses scikit-image to make their source catalogs. And in medical image processing, scikit-image is used in various places. This example over here is a piece of work I did with a friend of mine, where we calculated when cement injection is done to refixate hips, which amount of cement ended up in the cavities that they wanted to fill, and how much was still needed. This other example over there was the first piece of scikit-image that was built by a company contribution, and they sponsored the extraction of 3-dimension skeletonization in scikit-image. Here's an example from quantitative histology at Princeton. And finally, Robin Wilson submitted the satellite imaging example. So just to give you a feel for the wide variety of fields in which scikit-image is applicable. All right, so let's get into it. Let's fire up the first notebook. So if you go to the, I'm just going to orientate you a little bit. So if you fire up your Jupyter notebook, you should please do it inside the root of the lectures directory. So when you fire up Jupyter, you should see something like this. Then navigate to 2017 SciPy, and that will bring you, and then there will be an index page, and this is the page that I'm now viewing. So from there, you'll be able to navigate to these individual lectures. Okay, if you can't find this page, just raise your hand, and one of the other instructors will come and help you out. Okay, so we're going to start most of the notebooks by calling matplotlib inline. That's just to make sure that when you make plots inside of matplotlib, they don't pop out outside of the notebook. And then we import scikit-image. So, like I mentioned before, scikit-image uses standard NumPy arrays to represent images. And let's start by building the simplest image that we can, which is a grayscale image, 2D grayscale image. So we'll import NumPy as NP. That's a standard convention. Import matplotlib, the pyplot submodule as PLT. And then we're going to generate an array. The array is going to be 500 by 500, so it's a square image. And it's going to be random values between the value of 0 and 1. And then we... oh, my font size again. Sorry about that. Is that better? Yeah. So we generate a random image, 500 by 500, values between 0 and 1, and we display that using matplotlib. And there's what you get, exactly what you'd expect. So the same holds for real-world images. That was an artificial one, but if we import the data submodule from scikit-image, it contains a bunch of test images. So for example, we can look at the coins data set. And I'm just going to display the type of the coins object after I've loaded it, its data type, and its shape. So you can see that the coins image is just a NumPy array. Its data type in this case is unsigned integers 8-bit wide, so that would be numbers from 0 to 255. And the shape of the array is 300 something by 300 and something. We can now extend this concept further and think, how would we represent color images? And what we typically do is we say a color image consists of a red, a green, and a blue layer. So it's essentially just 3 grayscale images combined into one. So you stack the 3 layers on top of one another, and you get an M by N by 3 array. That's your color representation. So at each row, column position, you have 3 values, red, green, and blue. So again, we're going to use the test data set, in this case, Chelsea, the cat. And if we look at that image, you see that the shape of that array is 300 by 451 by 3. And its data type is, again, uint8, so it ranges from 0 to 255. So since these are just NumPy arrays, nothing stops you from manipulating the array and thereby modifying the image. So if we were to take this array and modify, say, rows 10 to 110 and columns 10 to 110 and fill that block with the value 25500, what do I expect to see? A red block. Yes, exactly. So let's see if that happens. Yes, indeed. So we modified the array, redisplayed in matplotlib, and we see a red block come up. If you include a 4th dimension, so you've currently got red, green, and blue, but if you also include an alpha dimension, then you can encode transparency into the image. So like you know that PNG images often have like regions that you can see through, and you can do that with an alpha layer. You'll see this again later in the tutorials, but I wanted to highlight the different kinds of images you can represent. We've now seen a simple gray level image or grayscale image with rows and columns. We've seen a color image, rows, columns by 3 for RG and B. But you can also have a 3-dimensional volume that you can operate on. So that would be several planes, each consisting of a rows by column image. Or you can have a 3D multi-channel image which would have planes, rows, columns, and then 3 different channels like red, green, and blue. future versions of scikit-image, we might incorporate temporal data, and then those dimensions would be added in addition, but we won't go there for now. So we've now seen that, yes, go ahead. So the question was, are the RGB channels always 0 to 255? So that's an important point. Scikit-image allows you to represent images using different data types. We've so far seen that if I generated an array with NumPy random that had values 0 to 1, that somehow worked. But when I loaded images from disk, they had values 0 to 255, and that also seemed fine. And the reason why is because we've got, we know what to expect from the different data types. If your array has a data type of uint8, we expect the values to go from 0 to 255. If your array has a floating point data type, then the values must range between 0 and 1. And scikit-image always interprets it that way. Internally, however, most of scikit-image functions on floating point images. So we typically, when we ingest images, we convert them to floating point ranging between 0 and 1, and then operate on those images. So when you construct a pipeline of imaging functions, if you send uint8 images into scikit-image, you might get floating point images out. But there are utility functions for converting between these different representations. So here's an example speaking to your point. I'm going to use NumPy's linspace. I'm going to take 2,500 values between 0 and 1, and I'm going to reshape that into a 50 by 50 block. Then I'm going to do the same, but take values between 0 and 255, reshape them into a 50 by 50 block, and cast them to uint8. So let's see what happens. Okay, so there you see that those are both valid representations of the image. The first image has got is a float 64 image, a double, and it ranges from 0 to 1. The second is a uint8 image, 0 to 255, both valid. Is that clear? Are there any questions about this concept? So I mentioned that there are these conversion functions that you can use to convert between the different representations. So from scikit-image, you can import image as float and image as ubyte, which stands for unsigned byte. And if you call those functions on an image, you'll see that it converts it between the different formats. So if I call image as float on an image, it again has a range between 0 and 1. If I call image as ubyte on an image, it ranges between 0 and 255. The only reason I'm emphasizing this is because it's very common to run into situations where you think you're setting a value between 0 and 1, but you're actually working on an image that ranges between 0 and 255, and it can cause complications. So I'd say the simplest workflow is just convert to floating point image first, and then work on that. Right, so we've now already seen how to display images using matplotlib. Those of you who've used matplotlib may be familiar with this syntax already. It's if you want to create multiple plots next to one another, you can specify the number of columns. For subplots, you could also do it like this: number of rows, number of columns. And matplotlib will give you a figure with 2 axes, and you can draw on those axes. So let's take a look at the cameraman. So I'm going to talk a little bit about this color map, just because it's used so often, and often with such devastating effect, not for the positive. So let's take this image and just zoom in on the man's face a little bit. So just take a look at that. So do you see all the artificial contours introduced on the left-hand side? Like, that's not real. But that's what we see when we use this specific color map. So Matplotlib has now changed its default. It's using Viridis by default, which looks a lot better. But I still have this warning in place because I see a lot of papers being published with this specific color map. But all right. I'm going to show you one more example of that. I'm going to create a grid of numbers between -5 and 5 at intervals of 0.1. I'm going to create, do you know the np ogrid command? So ogrid stands for open grid, and it basically creates two vectors for you. It creates a row vector and a column vector. The row vector goes from -5 to 5. The column vector goes from -5 to 5, and it allows you to set up a grid like I'm doing here. So I've got my x coordinates, I've got my y coordinates. Now I'm going to calculate the radius from the center. I do that by using broadcasting in NumPy. So I say x squared plus y squared, and I just scale that by 15 to shrink it in a bit. Yeah, so the exponent of -x squared plus y squared over 15. Let's plot that function. So there it is with jet, and you can see very clear ringing on the side as well. So in the notebook, you'll see commands for changing the default color map. Like I said, that shouldn't be necessary in later versions of Matplotlib, but you can see that that ringing goes away completely when you use different color maps. So I'm not going to talk about this any further, but if you scroll down in the notebook, you'll see that there are examples where you can play around interactively with the different color maps and see their effect. So you'll see this widget where you can adjust the color map and the interpolation and see how those two factors influence image display. Right, so far we've generated arrays from scratch by using NumPy's random command, and we've loaded images from scikit-image.data. But it wouldn't be very useful if we couldn't actually load data from disk. So scikit-image provides an I/O module, and while the underlying implementation changes a little bit from time to time, the I/O interface is stable. So you can always do from scikit-image import I/O, io.imread, and the file name that you want to load. So for example, in the current repository, I've got an images directory with the balloon image in it. So let's go ahead, read that image, and again, we'll see that it returns a NumPy array, and we'd expect that array to have the same properties as we've seen before. Indeed, it's a NumPy array. uint8 ranges from 0 to 255. If you launch the notebook inside of the lessons or the lectures directory, this file path would be images for you, so just in case you can't find that image. Who was able to load this image? Okay. If you had any issues at all, just raise your hand, and Claire will give you a hand. Scikit-image also has the notion of an image collection. So that's when you want to load a whole bunch of images. Image collection is very much like a list, except that it's a bit smart about how it loads the images. So it will only load one image at a time unless you tell it that you want all of them in memory at the same time. So it's quite safe to do something like tell it to read all the PNGs or all the JPEGs in the directory. It won't immediately do anything. You'll see it just gives you back an image collection, and when you print that image collection, you just see a list of file names. Only once you index into the image collection does it go and load the images from disk. So for example, I can create subplots. Here I make the number of columns equal to the length of the image collection, so the number of images I've got available, and then I just display them one by iterating over the image collection. So for I, image in, who's familiar with enumerate? Yeah, to show you what that does. So when you enumerate the collection, it gives you the index into the collection and the item. So it will give you 0 and the first item, 1 the second item, 2 the third item, etc. So in this case, I say, please enumerate my image collection, and on axis number, say 0, display image number 1. On axis number 1, display image number 2, etc. So there we go. And all the images get loaded from disk as necessary. Okay, so let's do a quick exercise just to practice manipulating NumPy arrays. So the first exercise here is just to take an image and to draw the letter H on it. So that requires taking the image and manipulating the underlying NumPy array, or manipulating the image NumPy array, same thing. The interface is draw an H on my image. I give you the coordinate at which you should draw it, the color of the letter, and whether it should be in place or not. In place means take the image, modify the values. If it's not in place, take the image, make a copy first, and then modify the values. So here's a template that you can fill out. The second exercise is to do an RGB intensity plot. So I'm going to give you a color image, an M by N by 3 image. And your job is to, at a specific row of that image, take a slice of the image and display the red values, the green values, and the blue values. So image, slice through the image, and make a line plot of red, green, and blue. And the third exercise there, if you have time, is it's a one-liner just to convert an image from color to gray, so from RGB to gray. So commonly, it is thought that you can do that by just averaging your red, green, and blue channels, but because luminance depends differently on the different color components, you actually need to weigh them. So you need to take 0.2 of red, 0.7 of green, and 0.07 of blue to convert from RGB to gray. So I'm asking you to do one single matrix multiplication to take a color image and convert it to gray. Okay, so we'll take 10 minutes to do that, and then I'll take 5 minutes to run through the solutions. All right, let's take a look at the solutions to those problems. So in your Jupyter Notebook, if you go to Lectures and Solutions, we're looking at 0, 0 images or arrays. So the first exercise was to draw an H on an existing image. There are many ways to do this. I just chose one way, which was to take the image and slice out the area that I wanted to draw on. I called that my canvas, and then I filled in the pixels on there. You could also calculate the offsets and fill them in on the original array directly, doesn't matter. But what I did was I said canvas is the first row coordinate, and I slice from there to that same coordinate plus 24. So that gives me my 24 high. And then the column coordinate to the column coordinate plus 20. That gives me the 24 by 20 block that I want to work on. And then on the canvas, I say make the first, take all the rows and make the first 3 columns that certain color, and the same at the end, and then draw the middle bar. Okay, so there's Chelsea with a little h on the side. Who got to this one? Yeah, good. So I want you to plot the red, green, and blue intensities of a specific row of a color image. So I want to separate out the red values, the green values, and the blue values. So I slice the image, the NumPy array, at that specific row. So remember, my dimensions are rows, columns, and then depth, or color layers. So I'm slicing it at a specific row. I'm keeping all the columns, and I'm grabbing 0 for the red values, 1 for the green values, or 2 for the blue values. And then those are one-dimensional arrays. So I plot those in the colors RGB. So there you go. Here's another slice. Yeah. The final exercise was to convert the color image to black and white. Like I said before, that's a one-liner. You just because it's just a NumPy array, you can do any linear algebra operation on that array. So it's an m by n by 3. We'll multiply it by this vector of weights. And so it's mainly to illustrate the new matrix multiplication operator that appeared in Python 3.4, 3.5. So that one line gives us a gray level image. There we display 2 gray level images. One was obtained with our matrix multiplication. One was obtained using scikit-image.colors built-in function RGB to gray. And you see they look very similar. In fact, when I rescale the images, because my cat image is 0 to 255, so I scale it back to 0, 1, and I compare that image with the one calculated by RGB to gray, we'll see that the mean error is very small.
Okay, is everybody able to find this tutorial? Cool. I would love to, but we're going to be looking at images that are fairly large, and I think it will end up cutting off some of the images. Do you have the tutorial running locally on your laptop? Okay, great. So for the last year or so, I've been working on 3D image processing as it pertains to biological data, largely neurons and cell membranes. And fortunately for me, at the same time, the scikit-image library was in the process of adapting their own algorithms to support 3D. So this is sort of an overview of the work that I've been doing for the last year for 3D image processing and sort of the tricks and the tips that I've learned. At the very top is an introduction to what are 3D images in scikit-image, which has already been covered, so I'll just go through it briefly. At its simplest, a grayscale volume is a 3-dimensional matrix. In practice, 3D images aren't pure volumes, and this is largely due to the way that they are captured. In the cellular data that we'll be looking at, the cells the microscope imaged the cells by kind of changing the focal depth, thus like generating that stack of 2D images where every image was one image was taken here, another one was maybe taken here, and so on throughout the stacks. There's quite a bit of a gap between the image planes. Folks who are working on tissue might thinly slice their tissues, and so they'll have kind of a more finer depth between their slices, but that scaling is still much larger than what the actual camera sees in those rows and column dimensions. So this data here was provided by the Allen Institute for Cell Science. They were my collaborators in developing 3D support, so I'm going to give them a shout out. We'll see that the shape of this image is 60 pixels, or 60 planes of 256 by 256 images. It's got a float 32 as its, or float 64 as its data type, and naturally it's scaled to 0 and 1. One thing that I will mention is that for the purposes of this tutorial, I've downsampled the image by a factor of 4 in the row and column dimensions. So the original image size was 60 by 1024 by 1024. Unfortunately, 3D image processing requires quite a bit of memory and time to compute, and so we don't think we'd be able to get through as much data in this tutorial if we'd use the full image. I chose not to rescale it in the plane dimension since the amount of information, we only have 60 slices, is so far. If we were to quarter that, we'd lose a lot of valuable information. So the distance between the pixels in our image are actually reported by the microscope that's used to image the cells, and I was able to get that data out by looking at the metadata in another application known as ImageJ. I've copied that to a variable here we called original spacing. So the original image was 0.29 microns by 0.065 by 0.065. To adapt for that rescaled image, I've multiplied the spacing in the row and column dimensions by 4, and then normalized it so that the spacing in row and columns is 1. So our final image spacing is 1.1 by 1 by 1. We talked earlier about visualizing volumes using IO-imshow. So let's go ahead and give that a try. Surprised it doesn't work. Volumes can't be displayed with imshow directly. It's really only used for 2D grayscale and RGBA images. But we can use it to visualize planes, and there are kind of 3 views that we can get on our volume. We can get our top-down view. You can get sort of what I'll call a left-to-right view and a front-to-back view if you think about our cube. And you get this by fixing one axis and letting it vary over the others. So if we take a look at the data here, this is kind of the data as the camera captured it, looking top-down, and then the fixed row and column views would be our left and right and our front and back views. So to get an idea of how this volume looks like over the whole scale, we can generate kind of all the planes that are available to us by printing out all the slides. So let's take a look. So this is our full volume, kind of as the camera sees it, with that top-down view. This is the nuclei channel, the nucleus channel of the image. I've chosen for this tutorial to display the data kind of looking at those image planes because that gives us the most information per slice and also was how the image was captured. You could also iterate, left to right or back to front if you wanted to look at those side views. So our goal today is to segment this image. So we want to identify and assign a unique number to each nucleus in the image. We'll do that by following a series of steps which will enhance contrast in the image, giving us a better distinction between the foreground and the background. We will denoise the image to get rid of spurious fragments, bits that are wrongfully bright or wrongfully dark. We'll also binarize the image, and then we'll apply our labeling. And once we've got a good segmentation, I'll walk you through feature extraction for 3D images. So we'll notice that the contrast of this image is quite low. The cells appear very dim against a dark background. And what we want to do is try to make those cells really pop, make them a lot brighter. The scikit-image exposure module contains a number of functions for enhancing the image contrast. These operate on pixel values and generally do not require any sort of information or care about the shape or the spacing of the image. So one such function for correcting or for enhancing contrast is gamma correction. It's also known as the power law transform, and you can use it to brighten or to darken an image. A gamma less than 1 will brighten the image, and a gamma greater than 1 will darken it. We see that we've applied adjust gamma to the entire volume, while I've only displayed slices here in this visualization due to rather limited screen real estate with the large image. Underneath each image is the histogram of pixel intensities across the entire volume. The original image on the left kind of shows 2 spikes. The first one corresponds to the background pixels, and the smaller one, kind of centered around 0.2, corresponds to the foreground pixels. And in general, we see that most of these pixels are kind of shoved towards 0, making it very dim. When we applied gamma correction of 0.5, we sort of shifted that entire histogram towards the center, or towards 1. But the distribution has kind of been kept the same. We see that the cells in the image appear brighter, although there is some increased background noise where those pixels were enhanced. The gamma of 1.5 shoved everything towards 0, and we've darkened the overall image and lost a lot of the structure of it. In addition to gamma correction, there's also histogram equalization, which improves contrast of an image by redistributing the pixel intensities. The most common pixel intensities become spread out, which allows areas of local low contrast to gain a higher overall contrast. As you saw, this operation is quite fast, but it has the downside of enhancing background noise. And if we take a look at the image, we see that the planes near the top and bottom of the stack kind of look like your old TV when you turned it on and it couldn't find a channel, and it made that awful sound. But the cells in the middle, the nuclei in the middle appear quite bright, but the background noise around them, there's a lot of salt and pepper noise there, which is not particularly desirable. I've highlighted the spreading out of this histogram equalization result by plotting the original and rescaled histograms along with their cumulative distribution functions. And we see that linear line in the equalized function, which sort of indicates that the same amount of intensities are binned at each bin in the histogram. So we've got a much nicer spread than the original function. Probably the simplest way to enhance contrast is to kind of just oversaturate the pixels at the extremes of the endpoints. A few really bright artifacts can kind of shove all the intensities down and make the rest of it appear quite dim. A lot of experimental data is kind of pestered by such noise. So here we've removed the brightest and dimmest 5% of the pixels and rescaled the image to 0 and 1. And in fact, we do see quite bright nuclei against a darker background, and the noise has not been as augmented as it was by some of the other operations. Any questions about histogram or contrast adjustment? Cool. Let's move on. So at the end of each of these sections, I've got a little bit here that sets an operation to a kind of more general name, and we're going to pass this on to the next function or the next set of operations and kind of feed the result down through to get to our segmentation. For now, please just leave these as is, but when we're coming back to the challenge problems, you may find it useful to kind of see the effects of different operations as they pass through the tutorial. So this next section on edge detection is kind of meant to highlight some of the differences between processing whole 3D, or sorry, it's meant to highlight the differences between algorithms that work entirely in 3D and algorithms that are adapted for 3D, or that we've kind of faked to get a 3D result. Edge detection highlights the regions in the image where a sharp change in contrast is occurring. So a bright edge corresponds to a sharp transition from a bright region to a dark region, and a dim or non-existent edge indicates more gradual or no change in intensity. The Sobel edge operator kind of approximates the gradient of the image, but is faster to compute. It has not been adapted to 3D images, but we can approximate it by applying it plane-wise to get a 3D result. And this is what you see here in this section. We initialize kind of a placeholder using np-empty. You could also use, you could also use np-zeros to initialize sort of an empty image, and then we compute the operation on each plane and save it back to that kind of placeholder to get the result. So let's take a look. Might be difficult to see on the projector, but it's easier on your screens, I would hope. The edges of the nuclei appear to be very bright. They've got very bright rings around them. The centers are a little bit splotchy, and that's due to kind of some natural variation within the nuclei. And the background appears quite dark. In this next pane, however, we're comparing the difference between the operation applying plane-wise to approximate the 3D result and what the actual operation looks like applied to that particular plane. On the left is the 3D image operation, and on the right is Sobel applied to that particular slice. And you can kind of get a sense of how in the 3D approximation we weren't able to fully detect all of the edges in the cells in those views. So this is just sort of a careful gotcha, something to consider when you're processing 3D images. So the Sobel operation was a filter. Filters are useful for other things beyond detecting edges. They're really good for smoothing images and for denoising, so removing salt and pepper noise. The Gaussian filters applies a Gaussian function to the image, which creates an overall smoothing effect. It takes as input a sigma, which can be a scalar or a sequence of scalars, and this sigma corresponds to the standard deviation of the filter along each axis. When we deal with volumes that are have a dimension that is the resolution is greatly reduced, we want to adjust our filters such that the contributions of the pixels above and below don't have as much as a role as the contributions in that same plane, just because they're spaced further apart. So we can add for that by taking our base sigma of 3 and dividing that by the spacing before applying our Gaussian filter. So we can see that our cells are quite blurry, quite uniform. One kind of undesired effect here is that the edges of our cells have now started to bleed into the background. And when we're doing image segmentation, we want to keep a nice kind of crisp edge, that we want to keep that definition between the foreground pixels and the background pixels. Otherwise, we may detect nuclei or cells that are kind of bigger than they actually are. So there's other filters for doing that. One such filter is the median filter. It's really great at removing salt and pepper noise, and it can preserve the edges in the filter, or the edges of the objects. It's not adapted to 3D images, so we will apply it plane-wise. Additionally, it expects your data to be UN8, and it's going to whine about that, the conversion from float to UN8 a little bit, but we end up not losing so much data, as you'll see here. So we still have these nice crisp boundaries between our foreground and our background. It's hard to see in this full plane view, but in just 2 cells, we'll see kind of a side-by-side comparison. You'll be able to observe the reduced noise that occurs in the central planes between the cells. Similar to the median filter is the bilateral filter. It's actually in the restoration module of scikit-image. It's an edge-preserving and a denoising filter. It works similarly to the median filter, but it can also, in determining like the value per pixel, it can also take into effect kind of space and color. It's not yet adapted for 3D, so we'll apply it plane-wise. But one interesting thing about the filter that I want to point out is this multi-channel parameter. We also saw this in the Gaussian filter here. And this can lets the filter function know whether or not the data is multi-channel, and can actually be quite helpful in determining whether or not you've provided it a 3D grayscale volume or a 2D multi-channel volume, because the dimensionality of those and their NumPy arrays representation is both 3. So if we take a look here, we can kind of compare the 3 different results. Gaussian filter looks very blurry. The median and bilateral filters appear very crisp. And if you look closely between the cells, some of that salt and pepper noise has been reduced, which is desirable. For fun, we'll pick the bilateral filter as our denoised image as we move on to the next step. So we've now improved the contrast in the image, and we have done some denoising. The next thing that we want to do is threshold the image, and this creates a very simple segmentation of the image where the true values or the white values of the image will be the foreground, and the false or the black background or the black values will be the background. In thresholding, a value is used to determine the intensity value which separates those foreground from background. Within the filters module, there are a handful of thresholding algorithms. Probably 2 of the ones that I've found to be the most useful are Otsu's method and Lee's minimum cross entropy thresholding. These work on full volumes as well. So on the left, I've plotted the histogram of the denoised and rescaled images. In red is Lee's threshold value, and in blue is Otsu's. And both of them have kind of picked a value that is settled between those 2 kind of modes in those distributions, where the peak around 0.1 is sort of where all the background pixels lie, and the peak around 0.42 is where all the foreground pixels lie. So our threshold, we want a threshold value that's kind of right in between those 2 peaks. Lee chose 0.26 and Otsu's chose 0.37. And in comparing the 2, just comparing slices side by side of these 2 images, we see that Lee's done a pretty good job of picking out whole cells. Otsu's looks a little more chunky. There are more holes in those cells where the region of the nuclei were a bit darker. So if we look at Lee's, if we look at the result for Lee's thresholding, we still see a fair number of cells which have kind of missing interiors. In the kind of upper and lower planes of our image, there's some speckle noise. And our goal is to, or what we would like to do next, is to remove some of that speckle noise and also fill those holes in. We find that morphological operations are quite useful for doing this. The morphology package within scikit-image defines a number of structuring elements, which are just kind of shapes over which a filter will be applied. The response to that filter indicates how well a neighborhood corresponds to the structuring element shape. So there are 2- and 3-dimensional structuring elements in the morphology module. The ones I most commonly use are the disk, whose 3D counterpart is the ball, or the square, whose 3D counterpart is the cube. I haven't visualized these, but if we initialize them and check their shape, we could observe that these really are 3 dimensions. So morphology is essentially combinations of applying an erosion or a dilation to an image. Dilation will enlarge bright regions while erosion shrinks them. All the other morphology operations are sort of built upon these two. For example, the closing of an image is a dilation followed by erosion. It's really useful for removing dark spots. Its counterpart is the opening, which is an erosion followed by a dilation. And that is good for removing kind of the salt noise in an image. All of these are compatible with 3D images and 3D structuring elements. You cannot, however, apply a 2D structuring element to a 3D image and vice versa. So here are kind of those four operations applied to the image by using a ball of radius 3. And we can see that erosion does make the dark regions darker, dilation makes the bright regions brighter. Closing and opening as well. Closing kind of closes up those cracks, and that's pretty apparent if you look at kind of the chains of cells. They're now kind of touching and grouped together, whereas an opening, they've separated out a bit. Each of those four operations have a binary counterpart, which is meant to work on binary images and can be faster to compute than the grayscale operations, and so I've displayed their results below as well. So I mentioned that the morphology operations can be chained together to denoise an image, and we wanted to get rid of some of that speckle noise, and we wanted to fill in some of that, some of the holes in the nuclei. So to kind of show you a dramatic example of that, I've binarized the histogram equals equalized image, which was quite noisy, quite littered with salt and pepper noise, and then applied the closing to the opening of each image, one using a ball of radius 1 and the other using a ball of radius 3. I'm only showing this to you again per plane, although the results were computed per volume, kind of just due to the screen real estate. And we can see that even a ball of radius 1 removed most of that speckle noise, but each one kind of distorted the shape of the original image. The distortion is kind of worse or more visible when using a ball of radius 3 as compared to a ball of radius 1. So there are operations that we can use to kind of clean up our binary image without changing the overall structure, and these operations operate on the connected components, so regions that are all connected to each other, and it has the results of kind of preserving the larger shapes. So there are two functions within morphology for doing this. Remove small holes, fills holes, and remove small objects, removes the small bright regions. Both of these functions kind of take a min size parameter, and at first this was a little bit confusing to me because I would set the min size to be 10 and nothing would happen, and I'd set it to 1,000,000 and all of a sudden it would work. So it's the minimum size in total pixels of the accepted holes or objects, and my trick for this is to approximate a cube that kind of fills the region. So I look at the plane and I think, okay, this is the width of the hole that I want to fill, and then I multiply, and then I raise that to the power of 3 to get the total area as a cube. So first we'll remove the holes, and we see that each cell now appears to be filled in. There aren't any kind of little gaps. You will see gaps near the top and bottom as they disappear kind of into their murky abyss of whatever they were sitting in. But these aren't exactly holes. They're kind of more craters or cups. The holes were the regions inside the cell that were fully surrounded by pixels. Likewise, with remove small objects, in those kind of top and bottom planes, we've now removed those little speckles that were falsely detected foreground pixels that belong to that kind of murky sort of region at the top and bottom. When you start to see the cells appear or disappear, we do get speckles, and the reason why, same reason why those holes at the top and bottoms of the nuclei didn't disappear. Same with those speckles, because they are connected to larger regions in the planes above or below them. Cool, so now that we've got our pretty sweet looking binary image, we're ready to assign each region labels and kind of learn more about the cells that we have. So image segmentation partitions images into regions of interest. Integer labels are assigned to each region to kind of distinguish them. We can go ahead, as I mentioned, thresholding is a very simple form of image segmentation. It's a separation of the foreground pixels from the background pixels. And so if we apply the measure label function to our binarized image, we can get a sense of like what's being detected and what's getting labeled. Each color in this image corresponds to a different label. Let's look closely at that upper region. We see in the rescaled image, which is very close to our original data, there are three fairly distinct cells. In our thresholded image, those regions were connected because they were very tightly coupled and closely connected. So perhaps in the threshold value that we chose, we didn't choose one such that that very tiny little dark crack between the cells was preserved. And now we've ended up with 3 cells that have been assigned 1 label. This isn't great. A better segmentation would assign different regions or different labels to the different cells. So we have a trick for doing that, and it's the watershed algorithm. It's really great for distinguishing touching objects. What you do is you place markers and kind of expand them outwards until they touch, and you say, okay, this is where we've got 2 distinct cells. It works by starting at the minima and filling those basins up, and kind of a really great example that somebody told me once was that you can think of it like filling an ice cube tray. You want to fill it up until you've got 12 little neat ice cubes and not one giant ice cube pool. So in order to place our markers, we're going to take the distance map of the image so that the points furthest from the edge should be kind of the centers of cells, and this will help us distinguish 2 cells from 1, because in the case where you have sort of like a pinch point, it's going to identify 2 maxima, instead of in the case where you don't have any pinch points, it should identify a single maxima. And we'll place our markers at those maxima and kind of fill them out using the intensity image or the rescaled image that we started with. So this take a moment, hang on, we'll get through it. Boom. So we've labeled the image again. We see a lot more colors. Let's go ahead and take a closer look at at those regions that we identified touching cells before. So in the top, we see those same 3 distinct cells that were all assigned the same label in the thresholded image, and we can observe that they were assigned different labels. In the bottom was another region that was a little bit questionable, so I decided to zoom in on it and take a look. We see that the 2 cells that were assigned the same label, sorry, I'm going to zoom up, are kind of in the center right of our image, and they are indeed touching the image boundary. And we're going to forgive ourselves for assigning these two cells the same labels, because when we go on to measure features, we tend to discard the cells that are assigned the same label, because we don't have the full picture there. We only have half of the cell, and it doesn't really make sense to make measurements on half of a cell. It's also just generally really hard to get a good segmentation of these 2 cells when we're looking for those peaks, those maxima in that distance map. But we were able to distinguish it from that cell that's sort of in the center of the image that's got its own label, and that's great. So the watershed algorithm falsely detected subregions in a few cells. We see here in these 3 especially, they were assigned 1 or more labels when they really should have just been given 1. Oops. Why did that happen? We can take a look at that distance map and where the markers were placed to kind of get a sense of what was going on. So the tiny red dots in this image are where the markers were placed. The background of this is the distance image. So the points furthest for the edge are the brightest, and the points closest to the edges of the cells are the dimmest. We kind of observe that the cells with one marker, the cells that were properly segmented, appear very uniform in their distance map, where the cells that were assigned multiple markers kind of don't have that same level of uniformity. And to me, that indicated that, well, maybe instead of the pinch point being on the plane this way, the pinch point was happening in another view. So I zoomed in on those cells in different planes, and indeed, we do kind of see an irregularity to them, a sort of lumpiness. Below are their distance maps, and you can kind of see how it might find two peaks. There are ways for dealing with this. Kind of one of the problems that we'll work through at the end of this lecture are how to deal with that. When we searched for peaks, we gave it a distance, kind of an indication of how far apart peaks were. This is something that you might want to adjust in order to kind of say we don't want to detect peaks that are any closer than this amount. So that's something that's fun to play around with, and you can see the effects as you increase or decrease this image on the resulting segmentation. But for now, we'll march forward, we'll say this is good enough, and move on to feature extraction. So feature extraction reduces the data required to describe an image or objects by measuring informative features. These can include things like area or volume, bounding boxes, intensity statistics, and these can be computed per object, or they can be aggregated across all the objects in an image to kind of get an idea of what the image is like overall. As I mentioned before, we tend to discard the objects that are touching the borders of the image because we don't have the full information about what's going on there. It doesn't make sense to measure them. And within the segmentation module is a clear border function, which will only return the interior labels. So above the image, I've listed out all of the labels that are kept, that are the interior labels. And we'll see that they aren't sequential. We've got objects 1, 3, 5, 6, 7, 9, etc. One thing that you can do if this doesn't sit well with you, or if you want to be able to better, very easily index your objects, you can relabel the numbers sequentially. So now we've got all of our cells are assigned a label between 1 and 17. So we've gotten the segmentation, we've cleared the border, we're only looking at the cells that we're interested in. How do we learn about them? Within the measure module is something called region props, or a function called region props, which automatically measures many of the labeled image features. You can also provide it an intensity image, so it can collect those per object intensity statistics, such as mean, max, and min. It's good practice to make those measurements on the original image, which is why we've passed in data and not rescaled or denoised one of those other kind of images that we've manipulated. Disclaimer, not all of the properties are supported for 3D, but a lot of them sure are. So below is a list of kind of what is available out of the box for you without having to do a lot of work. And our supported properties include area, which is total pixels, so it's kind of our volume in total pixels. We've got B-box, which is our bounding box. There's also things such as those intensity statistics, that min, max, and mean. One of the nice things about region properties is that it automatically ignores that 0 label. So if we look at the region properties is a list, there's one per object, and if we call the label property on it, we'll see that we only have measurements for labels 1 through 17. We didn't collect any information on the background, which is just fine. To kind of get the properties out, you can call .prop or access it using kind of the dictionary or hash notation to access those extracted properties. So you could call .area or area. And let's take a look at that. So I've printed out the total pixels or the volumes for each of those labels. And those are just saved as a list. You can synthesize this data further by computing per image statistics, such as like totals, minimums, maximums, means, standard deviations, kind of anything you could think of. A lot of this is available in NumPy. Your more kind of complicated ones are available in SciPy statistics or scipy.stats. So here are sort of kind of the aggregated statistics per volume. One thing that was kind of a little bit noticeably lacking up here was the perimeter statistics. But we can compute the perimeter by generating kind of a mesh and then computing the surface area of that mesh. There are two functions for doing this within the measure module. One is marching cubes, which generates the vertices and the faces of our mesh. And the second one is the mesh surface area, which uses those verts and faces to compute the surface area. Marching cubes takes into account the spacing to correctly compute that spacing. If we just give it a spacing of 1, which is its default, that will give us kind of the total number of pixels, whereas if we give it the spacing of our image, the true spacing we computed earlier, it is going to take into effect that greater plane dimension and adjust the verts and faces accordingly. So we do see that the total pixel surface area is 88,000, whereas when we incorporate the spacing, it's 94,000. And this didn't make it into the tutorial, but I'll push it up after this. Wanted to highlight the bounding boxes that you can extract per object as well. This is incredibly useful for machine learning and for deep learning because you can quickly export per image, kind of per object crops of your images. Here's an example of what that looks like. So this is one of the nuclei that we were able to detect in our image segmentation. Cool. Can I answer any questions from anybody? Awesome. So I've got 2 challenge problems for you to work through in the next few minutes. The first one is to try to improve the segmentation, to get rid of that the over-segmentation of the pixels that we saw. I've got a couple of hints here that you can read through that might help you. If you're feeling like you want a really a harder problem to solve, then I would suggest trying to segment the accompanying membrane channel. So we looked at the nuclei channel, but there's also a membrane channel for these images. The membrane, I've got a picture down here that shows the membrane image and a membrane segmentation. The walls of the membrane are kind of that bright webby stuff. And so a good segmentation might look like filling that membrane in order to compute perhaps how large it is. I've got instructions for loading the image below here, which includes where it's saved. If you're wondering where should I kind of place those seed markers for my watershed segmentation, I will tell you that there should only be 1 nucleus per membrane.
All right, so for those of you not working on the segmentation problem, I'll give you another problem to look at. So this section is about ransack, the random sample consensus method. It's an iterative method that we can use to robustly fit models to noisy data, especially data with a lot of outliers that we'd like to reject. So let's see, so that's lecture number 5. You can find it just like the other lectures or from the index page or go into the lectures directory and click on 5 ransack. So ransack is located in the scikit-image.measure submodule. And I'm just going to generate some test data. It's not important how we do that for now, but it's important to see that this is how the test data looks. So you'll see that I've got a straight line. I added some noise around the straight line, and then I added some outliers in the one corner. So given this data set, what I'd eventually like to do is to fit a straight line to my data. I'm going to show you why that's difficult when you start off with data like that. So our model is the standard model for the line y equals mx plus c, where m is the gradient and c is the offset. You can also write that in matrix form. So if you take a vector of y coordinates, you can say all those y's are equal to all my x's in the first column, 1's in the second column, your two parameters mc in an additional vector. And when you make that matrix multiplication, it's just a bunch of x and 1's being multiplied by m and c's. So it basically just replicates that top formula into matrix form. So we basically have the formula y equals big X times p, which is an equation that we can solve. We've got many more coordinates than model parameters. We've got two model parameters here, m and c, but we've got many data points. So the system is overdetermined, and we can use least squares to solve it. So let's do that. We grab our x coordinates, we grab our y coordinates, we set up the matrix X by making the first column x's and the second column 1's. And then we use np-lin-alg least squares to solve for our parameters. And indeed, we get an m and a c parameter out. So with those parameters, we then plot the line, and look what we see. This is not surprising at all, right? Because what happens here is that we try and fit a straight line, and most of the data is in that big cloud. So if we didn't have the outliers, the line would probably have fitted correctly. But because of the cloud of outliers, it skews the line in the wrong direction. Now, scikit-image provides an n-dimensional line model. It's got a circle model, an ellipse model, various models that you can fit onto data. So let me show you that the line model just does essentially the same thing I just did with least squares. So from scikit-image.measure, I import this line model nd, and I construct the line model. I estimate the parameters of the model on my data, and when I look at the parameters, it's got some parameters that represent the line. In this case, it's a begin and an end point, and if you put a line through that, you get a line. So let's plot that. You see that each model has got a predict y coordinate. So if we give it a bunch of x coordinates, it will give us corresponding y coordinates. So there you go. There's the line fitted by the built-in scikit-image line model. Exactly the same as what we did with least squares. So the question is, how can I get rid of the outliers and still fit a model to this data? So Ransack is very clever and very simple. It says that how many parameters do I need to fit a line? Or how many data points do I need to fit a line? 2, because I want to estimate 2 parameters. So what I do is I take the minimum number of data points that I would need here, and I fit a line through 2 random points. So I'm just going to grab 2 points. Let's say I grab one over there, I grab one over here, I fit a line through it. It's completely the wrong line, but it doesn't matter. You fit the line, and you count how many of my data points lie close to this line. And then you repeat that procedure. You say, let's take another 2 random points, fit a line through it, how many inliers, how many of my data points lie close to that line. And you repeat that procedure over and over again, and you track how many inliers you have with each of these test models. And eventually, you choose the one with the most inliers, and you say, this is the best model for this data set. Yes, sir?
So do you have to tell it what you consider close, or can it sort of figure out what's the best?
The question is, do you have to tell it what you consider close? And yes, you have to specify. In this case, I would say that it's maybe a distance of 5 pixels or distance of, whatever. But you have to tell it what you consider to be an inlier and what you consider to be an outlier. So let's see how that works in this data set. So we call Ransack from the scikit-image measure module. We call it on our data. We say, please fit a line model for us. The minimum number of samples you have to take, 2. You have to pick 2 data points to fit a line model. Here's the residual threshold. That's what you were asking about. Distance of 10 from the line we consider an inlier. And run no more than 1,000 trials. The more trials you run, the more likely you are to run into a good solution. If you make the trials if you do too few trials, like only 1 or 2 trials, you're likely to end up with a very bad fit. We do have early stopping criteria as well, so if the algorithm sees that it's converging after a while, it will stop. All right, so let's fit ransack, and there we go. You see that with 1,000 trials, 1,000 different attempts to fit the line, that's the line that was found to have the most inliers around it, and it rejects the outliers that we were concerned about. So here's the exercise then, is in our solar system, the sun is a very spherical object, and I don't know the physics behind that. Maybe someone in this room does, but it just turns out to be a very spherical object. So let's load an image from the sun and display it. And what I'd like you to do is use ransack to fit a circle around the outside of the sun. So remember that I said we've got a circle model available. So I want you to plug that into ransack. Of course, you can't apply directly to this image. You first have to, well, what will you have to do? You'll have to do some edge detection on this image. That will give you an idea for where the outline of the sun is. But you'll also get a lot of edges around the ejections from the sun and around the interior. So you'll get the edge map first, and then you'll ask ransack to fit the circle model on the positions of those edge coordinates. So that's the other exercise that you can work on. We'll give you about 10 minutes for that and then run through the solutions. Just for the people who aren't very familiar with Jupyter notebooks or who just came out of the software carpentry, I'd just like to show you how to get hold of doc strings, because without those, you're probably not going to find help easily. So any function that you import, you can get the doc string in IPython by just typing a question mark afterwards and executing the cell. That will give you the doc string. And the docs, well, that's not a particularly, let's find a more complicated function, let's say from, so you type the question mark, you type enter, and you find a short description of the function, and then a list of all the parameters with their types and what they describe, and then a list of return values and errors that can be raised, as well as implementation notes, that sort of thing. In the later versions of Jupyter, you can also just type the Shift-Tab key, and the longer you keep typing Shift-Tab, the more insistent you are, the more help it gives you. So you hold Shift-Tab once, it starts telling you you want to specify these parameters. You type it twice, it starts to grow that window a little bit. You type it 3 times, and it's almost ready, and on the 4th time it pops it out for you. So that's another way to get to the help. Finally, you can also just go to the scikit-image website, and you'll find the documentation there, and you go to the API reference, and you'll find a list of all the different, the submodules are listed at the top, and then all the individual functions are listed down below. And again, it gives you the doc string just compiled into HTML.
Okay, so very quickly, I want to run through the solutions to the segmentation problems. These ones are kind of particularly tough, and if you played around with it, you might notice that the segmentation is rather sensitive to kind of the filtering or thresholding values that you choose, and but I think it was kind of important to highlight that for segmenting real-world data. So at the top here, I've just kind of copied in a lot of the display functions from the previous tutorial. So first we'll work on improving the segmentation. I've chosen to use the rescaled image where we clipped the brightest and darkest 0.5% of the pixel intensities. Likewise, I've used the bilateral denoising. I reckon that the sort of over-segmented cells was caused by this pinch pointing in kind of the row or column dimensions that we weren't observing, and I thought that if I perhaps gave it a more generous threshold, we would get kind of a smoother cells in those, or a smoother binary representation of those cells in the planes where they kind of start to disappear into their murky cell juice abyss. I'm not a biologist, so I don't know the real words for that. So I scaled the Lee's threshold by 0.9. So we get kind of more complete cells throughout the planes at the expense of generating maybe a little more noise that still isn't too hard to clean up with remove small holes and remove small objects, which I've combined into this step, still using that box with a width of 20. The image largely appears to look the same. Kind of this guy here that looks kind of like an S is a little more connected than before. So my next trick was to limit the planes in which markers can be found by kind of limiting the distance map that we're looking at. So I picked the slice of the binary image with the highest variance, so that was somewhere near the middle of the stack, and I'm able to kind of use this trick because my cells generally sit on one plane. I don't have kind of two layers of cells that I'm trying to segment. And once I found that that binary image with the highest variance, so the most kind of combination of the foreground and background pixels, I take 10 slices on either side, and I say, okay, let's only look for markers, or let's only compute the distance function and look for markers within these 10 slices, and that kind of just eliminates those rather kind of chunky, globby regions at the top and bottom of the cells, which cause the distance map to be non-uniform. So here's now kind of the binary image that we're searching for markers. Each cell looks nice and round. We aren't losing them as they disappear in the planes. And our final segmentation looks pretty darn good. That one cell kind of in the upper left that got put into two regions is dying. That one's actually going to be pretty tricky, a lot trickier to segment perfectly as one cell because it does appear as two very separate, disjoint regions. But we were able to, those cells in the middle that were over-segmented before, we don't have that over-segmentation problem here. So let's take a look at that membrane image. I'm going to apply that same rescaling. Ooh, that's gross. So it's pretty murky as we transition into the top of the membrane, and then we see kind of a nice membrane walls, and then there's a lot of speckly noise, which is either just kind of debris or some other part of the cell that adhered to the stain when it was imaged. And then the membrane wall kind of does not uniformly disappear. We sort of see this like sweeping from the bottom corner up to the right as it disappears. So this is a burden-generated, fairly rough segmentation. We're going to jump straight to thresholding the rescaled image. Looks pretty noisy, but we've still got a good idea of where the cell walls are, where the membranes are. I'm going to be pretty aggressive here and remove small objects plane-wise because we've got all these kind of blobs in the center, and some of the blobs that we don't want the segment end up kind of touching the membrane in higher planes and wouldn't be removed otherwise. So we've kind of cleaned it up at the expense of losing a few of those membrane walls, but our seeded image, when we apply the watershed, ideally will kind of meet where that wall once stood. There is some noise in these upper and lower planes that we would like to ignore, but I don't have a good technique just yet for cleaning that up. So as I mentioned before, there should be one nuclei per membrane, so we'll use the nuclei image that we cleaned up in the previous example to sort of work as the seeds for the segmentation. We don't want the membrane, since the membrane doesn't like kind of close evenly, as we see here, the cells will kind of like bleed through further than the membrane actually was. So the trick that I use to do this is I know that the membrane, there's no membrane on the last plane or the first plane, and so if I give those a seed, then that will kind of meet with the cells that bleed through, and I can erase those later to get to better kind of pocket the cells, to pocket the membranes in the image. So if we do that and display it, takes a minute. So we see that there was a little bleed through of the cells into those like upper planes, but in the central regions, we've done a really nice job of distinguishing each kind of membrane pocket corresponding to each nuclei. Cool.
Hello, and sorry for this little technical problems. I will start the part on image processing in machine learning. So if you go to the index, it's this third link, machine learning. You can click on it, and if you also have the Jupyter notebook that is opened in the lectures, in the root directory, so you can see that there should be, maybe I just need to refresh it. Yeah. I might, oh no, it's lectures, yeah. Lectures. There is a machine learning IPython notebook, Jupyter notebook, and there's a machine learning solutions one, which actually I should move to the solutions directory. So in the solutions, there are the solutions to 4 small exercises that we will cover during the tutorial. So each of them is pretty small. So during the exercise, you can either do the exercise or go out and take a break, get some snacks, and look at the solutions if you want to. So let's get started. So here is our notebook. So first of all, raise your hand if you already attended the machine learning tutorial or scikit-learn tutorial. So not many people actually, which is really good because it means that maybe you don't know that much more about machine learning than I do, because I come from image processing, not from machine learning. And so today we will see simple things about how to use machine learning for image processing, because Stefan and Claire already introduced to you some techniques of image processing that are signal processing techniques, but that are specific to the image processing domain. And machine learning, on the other hand, is something that is very generic. Machine learning techniques can process any kind of data as long as you can put them into an array of samples and features, as you will see. And therefore, we will be able to use very powerful algorithms by just fitting our image processing problem into a machine learning formulation. And bam, we will have one machine learning algorithm that will solve quite tricky problem for us. So I will start the tutorial with a very short introduction to machine learning. So of course this doesn't mean to replace a scikit-learn tutorial, which you should follow if you have the opportunity. So who already used scikit-learn here? So raise your hand if you, yeah, so. And so what do you use scikit-learn for? I'd be interested in knowing. Yeah, but which kind of machine learning? Machine learning, or usually it has some application, or is it research on machine learning, or yeah, Proto? Fraud detection. Okay, very interesting. Other applications?
Like analytics, predictive modeling for business cases, business intelligence type
Uh-huh.
internal products.
Business intelligence. All right.
Do a lot of satellite image classification, red ribbon classification.
Very cool, because now we're touching the field of image processing. So I think you came to the right place. So we've seen 3 examples, all of them being very different, from fraud detection, business intelligence, satellite imaging, classification. And that's the beauty of machine learning, is that for all this data you can use image processing. And so I'll start the tutorial with a very quick introduction to machine learning. So it's actually an adaptation of the scikit-learn quick start tutorial that you can find from this link on the scikit-learn documentation. And so I have written here some text to explain what is machine learning and which kind of problems it tries to solve. So in a few sentences, let's try to define machine learning as having a number of samples of data, and you know some things about this data, and then you try to predict the properties of unknown data. That's very vague, right? Very general. What's important is that you can put this in a mathematical way. That is, the n samples of data, they can be either one sample equal one number, one single number, or you can have more than one number per sample. It will be a collection of, say, m numbers. And then we will call this m numbers features, attributes, but we use the word features more, of the samples. And then, given this problem of n samples and m features, we'll have several typical machine learning tasks. So I just try to find an example. Let's see. I had found a very nice image on Google Image, but it was on my computer, and I cannot use my computer. Yeah, that was one. So you can either read this text. Are the fonts large enough for you, or should I increase them a bit? Yeah. So how can I do this?
Control plus.
Control plus. Thank you, Stefan. So classification is, say that I have a bunch of data. Here my data are 2-dimensional, x and y coordinates, and I know that some data are dots, other are crosses. I have already some data that are labeled, and then I look for the best separation between these two populations, which means that after, if I have some new data from this line of separation, I will know on which side to classify them. So this is called a classification problem. And if my data are not labeled at all, if I don't have any information about this point, about the group to which they belong, then I can do what's called a clustering problem. That is, I want to group, so forget about this line here. Say I only have the groups of points, and I want to find the best labeling that separates this point in two groups. So I would have one group here and one group here. This would be a clustering problem. And another very common machine learning problem is a regression problem, which is, for example, given this data point, find the best line model that fits this data. So these graphical examples are quite convenient to see the typical operations that one would like to do in machine learning. And this is explained also here in text. So classifications, we want to learn from already labeled data how to predict the class of unlabeled data, give a label to some data. So for image processing, how can we transpose this? For example, if we're given examples of pixels belonging to an object of interest, so pixels belonging to foreground and background, can we have an algorithm that labels all the other pixels of the image? That would be a classification problem. Or given images of cats and dogs, can we label automatically other images of cats and dogs? As for clustering, clustering groups together similar samples. So if I take all the pictures from my holidays, can I apply an algorithm that will group them automatically by subject? Subject meaning people, monuments, animals, and so on. So in image processing, a sample is just a collection of numbers, an array of numbers. So it means that it can be several objects. It can be a whole image, for example, because if I flatten my image into the vectors of all pixel values, then I have a feature vector. But a sample can be also a pixel. If I take its RGB values, it's a triplet, which are the different features of the pixel. Or a sample could also be a labeled region. For example, in the example that Claire showed at the end, when she used the label function for measure to label the different cells, and after to compute the properties of the cells. These properties, like the area, length, and so on, they can be features. So there is not one single formulation of machine learning for image processing. The first question to ask is, of course, which kind of image processing problem do I want to solve? But after, what will be my samples? What will be my features? So we will start by using a small example from the scikit-learn documentation, just to define our first estimator from scikit-learn to be sure that we know how to do machine learning. And you will see it will be very easy. So we will use a data set that's already provided by scikit-learn. So scikit-learn is the machine learning module of Python that is meant to work with NumPy images, NumPy arrays, sorry. So scikit-image is for processing images as NumPy arrays, and scikit-learn also works with NumPy arrays. And as you will see, the fact that both packages use NumPy arrays makes it very convenient to have them working together. So let's start by importing some submodule from scikit-learn, and then we load the dataset. So here I have this object digits that I printed out to see what's inside. So it's huge. It will clutter your screen. Sorry about that. But as you can see, it's a dictionary-like object which has several keys. So for example, I have this data object that looks promising. So it's a NumPy array. So if I ask for its shape and for the shape of the digits.target object, then I see that I have 1,097 samples, and each of them has 64 features. And there is this other array, which is a target array, which corresponds to the class of each data sample. So what are these data? It's not completely obvious. The best way is to represent them. So for example, we take the first sample, so data 0, and it's actually an 8x8 image. So we will just display this image. Okay, so you see that it's actually a very low resolution image of a number, of the number 0. And this dataset provides a lot of these small images that are all rescaled on the same scale, but they correspond to handwritten digits that were, I think, scanned by the US Post Office or something like that, so that we can use this dataset for the recognition of handwritten digits. So is it possible from this very low resolution images to predict the actual number that was written? That will be our image processing problem, and it's an image classification problem, because for each image we want to put the sample into a bin, say it's a number 0, 1, 2, it's a discrete number of labels. So to do this classification, we use one of scikit-learn's estimators, which is called SVC, Support Vector Machine Classification. And we will first have a training step from which we will learn a model from a fraction of the images that are already labeled. That's how we will train the algorithm. And after, we will predict the number of data that were not in a training set to see if the prediction is right or not. So let's first create the estimator. So it's this SVC object from the SVM module. And all scikit-learn estimators, whether classifiers, regressor, and so on, they have a similar syntax. The API of scikit-learn is very simple. It's object-oriented for the estimators, and after they have a few methods that are the same for all the objects. So for example, here I create my SVC object with some parameters that I won't spend time to define them. I will just consider the estimator to be a black box, but we can do this here. And after I created it, so I didn't pass it any data yet. To train the estimator, I use the fit method, and I train the estimator with all the data but the 10 last one. I will keep the 10 last ones to check whether the prediction is good or not. So, I fit the model with the data and the target values. That's the learning step. And after, I can predict the target value of new data using the predict method. So here I use the last two samples that were not used in the training set. It's very important when you check that your estimator does the right job, not to use data that you use for the training set for the prediction. Otherwise, you will have what's called overfitting, and your results will be really good, but if you give the algorithm new data, sometimes the result will be awful. So never use data that you use for training for prediction after. That's one of the very important rules of machine learning. So when I do this, I can see for my two images that the prediction was right. At least if you would agree that this is an 8, it's not completely obvious to me. So we did our first machine learning example. Yeah! So in the following, we'll cover several image processing tasks using machine learning methods. And we will use different kinds of samples and features. I told you that a sample or feature can be several things for image processing. So we will start from low-level pixel-based features, such as the RGB triplet for 1 pixel. Then we'll move on to mid-level features like regions of interest, edges, corners, and so on. And finally, we will use segmented labeled regions as samples and their properties as features. So we'll have 3 main tasks that will be image segmentation. So Claire already covered a lot of image segmentation. We will see alternative methods that I'm not saying that they are better or worse. They can just be used sometimes in combination with what Claire showed, and it depends really on your images. Then we will have an example of panorama stitching, when you want to stitch together images that your phone took. And finally, we will classify labeled objects. So what we will not do today is what's called computer vision. So if you don't know computer vision, it can be defined as the automatic detection or recognition of objects like faces in an image, or knowing that there is a cat in this image, for example. So we won't do that. If you want to know more about computer vision, you might check some excellent tutorials about OpenCV, for example, which has Python bindings. So is anybody here using OpenCV? A few people, yeah, it's an excellent library, and it can be used also in combination with scikit-image because it has Python bindings. So it's really cool that there are these different libraries that can work together. And also what I will not cover, but what will be covered by Stefan after this part is using deep learning, because deep learning is nowadays a very important part of machine learning. It's very powerful, and it can solve a very large variety of problems. So it usually requires quite a lot of resources, both in terms of training time and also memory and CPU time. But you will see an example of image classification using deep learning with Keras libraries. So what we will see in this tutorial part is more simple. There will be small examples with different machine learning techniques. So we'll start with image thresholding, binarization, or what's called vector quantization. So it builds on the idea of image segmentation using only color information. One of the very first techniques that you saw during Claire's tutorial was to threshold an image using the gray values to distinguish the cells from the background. And for this, of course, you can set a threshold manually, but it's usually better to use an automatic thresholding algorithm. And you saw two different algorithms, which were Otsu and Lee. So let's do this again with the camera array. So here I compute the histogram from the exposure module, and then I compute the Otsu threshold. And what you see here is in yellow the boundary of the segmentation, and here the dotted line corresponds to the Otsu threshold. So Otsu is one of the tricks that everybody who does the machine learning, who does image processing should know. It's very important because it can save you a lot of time instead of looking at histograms and having visual inspection for finding the best threshold. But it only works for grayscale images. For example, if let's say that I create an RGB image using this Chelsea, and I ask for its Otsu. You see that I have a user warning saying that threshold Otsu is expected to work correctly for grayscale images. And actually for an RGB image, what the algorithm does is just to flatten the array so that all the different channels are mixed together. And so the resulting threshold will not make any sense. So you should never use Otsu for an RGB image. However, when you look at the histogram, you see that the idea of Otsu thresholding is kind of a clustering algorithm, because you try to group together pixels that have a similar gray value. So can we do this in, for RGB images? So when we want to do this, we want to transform our 1D clustering problem into a 3D clustering problem. That's all. And therefore, we'll use a clustering estimator that's called the k-means estimator. So who has already used the k-means estimator here? Yeah, so one third of the people. So it's really cool that you already know it. It's really the most simple clustering algorithm that's available. Oops, sorry. And the idea is just to group together samples, so that each of them is as close as possible to the center of its group. So for example, on this image, the center of each group would be here and here, and I will try that each sample is as close as possible to the centroid of the cluster. So you don't have to know how the algorithm works. I will really not dwell upon that, but we'll just apply the algorithm and see how it works. So before doing any image processing with the k-means, I just copied here an example from the scikit-learn documentation, which is a very simple example of k-means. So let me just execute it, and then I'll go through the code. So I import this estimator. It's in one of the submodules of scikit-learn, and I have this iris dataset, which are some properties of flowers, iris flowers. And once again, I have a data array and a target array, as we had with the digit dataset. Then I create this k-means estimator, and I tell it that I want n clusters equal 3, meaning that I will have 3 groups of samples. So this is just for visualization. And then I fit I use this fit method of the estimator, which will determine the labels. So here, I do not pass it any target values, because clustering doesn't use any target values. You don't give them labels. Its purpose is to find the labels. And after, when you plot the result, you see that the different colors correspond pretty much to what you would have done yourself manually if you would have to define 3 groups with these data points. Any question? So please, if something is not clear, if my French accent is too strong, or interrupt me, because that's, I mean, if you're in this room, instead of watching a scikit-image tutorial on YouTube, the reason of being here is to interact with the speakers and or with your neighbors and to ask questions. So I would like this tutorial to be as interactive as possible. So how can we use k-means clustering for segmenting our image? So we will use as a feature the color vector, but we will not do this in the RGB space. Why? So I will just, yeah. Why don't we use the feature vector in the RGB space? It's because in the RGB space we mix up information about color and lightness. In each channel you have both the color intensity and the lightness. And therefore, if you have objects of different colors, but that also have variations in lightness, then it might be difficult to cluster the pixels when this information of color and lightness are mixed. Therefore, we transform the image into a different color space, which is called the LAB. I don't know if it's called lab or LAB, you know, Stefan? But I think it's LAB. With the first dimension L, it's the lightness, and then A and B, they correspond to different directions of color intensity. I don't know if it's between red and yellow or something like that, but you don't have to know this to use this example. So I just load this image. Remember that we use this imread function of the IO module. And then I transform my image into the LAB color space. And I will use only the color channels. That is, I don't use the first channel, 0, which would be for the lightness. And then I create a k-means estimator, as we did for the iOS dataset, but for 2 clusters. And I fit it with my data. And then I have this labels underscore property of the k-means estimator. So let me just show you. It's an array of labels. So k-means dot labels. And it has non-French keyboard. It has 2 values corresponding to the 2 labels. And then I just have to reshape the flat array into the same shape as my original image so that I can visualize it. So here I plot the original image and the contour. So everybody is familiar with this contour function of matplotlib, or no? Yeah. So it, because my segmentation it has two values, 0 and 1, and therefore it plots the contour, the edge, which is here. So here you can see that k-means clustering works really well for this RGB image. And we use 2 clusters because for Otsu thresholding we had 2 populations of pixels, but of course this method generalizes to a different number of classes. And in the following example, I propose that you go through the remaining cells until the exercise here. So you should just execute these 2 once, look at the code, and here we use 4 clusters and the 3 channels L, A, B, and I want you to do the same with only the 2 color channels A and B and see how the result changes and to understand why. So we'll take 5 minutes for this, and of course you can also take a break. So I had a remark that this notation was not very clear, and it's me liking compact NumPy notations, right? And this was just meant to remove the number of channels from the image shape, because this segmentation array will be a 2D array of labels, so no channel information. And therefore, I wrote it here in a more readable way. If you were confused by this notation, maybe this might be clearer. Any other questions? So who has already finished? Yes. Who is having problems? Okay, so here is a solution. So here I switched to my solutions notebook, and so you see that this time for this chapel floor picture, we defined an estimator with 4 clusters, and we fit the data in the LAB space. And so what I did here is to use a nice trick that we have in the color module that transforms an array of labels into an image where each labeled object would have the average value in another image. It's it's a bit convoluted to explain it like this, but when you compare this image, you can see that here every segmented region has the average value that it had in the image im. So maybe it will be clearer if I just look at the docstring of this function. So remember, question mark, return an RGB image where color-coded labels are painted over images, but if we used kind equals average, it replaces each labeled segment with its average color. So here what I did was to do like a posterized version of the image. I don't know if some people here are using GIMP. You have this very nice filter that's called the posterize filter, and it outputs an image where you have only a few color levels. That's what we have here. We have as many colors as the number of clusters that we used in the classification. And so my exercise was to use not 4 clusters as here, but 3 clusters, and also to use only the color channels, not the 3 channels, including the lightness channel, which is the first one in LAB space. So what happens if we do this? So I just removed imlab 0 for the first channel, and 3 clusters. And what you see is that the white and black colors were merged together, because if you don't use the lightness information, actually white is a mixture of all colors and black is just the same but with a very low intensity. So that for our clustering algorithm, in the 2 color dimensions, these points were really close together. So does that make sense to you? Or? Yeah. So my point here is just to show you that when you design a machine learning problem, the selection of features is very important, because whether we use only the 2 color channels or the 2 color channels plus the lightness channels, our final segmentation is very important. So feature selection is a very important part of machine learning, and this is true for image processing as well. Okay, so let's move on to the next part. And we'll continue with image segmentation, but we will try to be, let's say, more clever this time, because when we used segmentation using only color information, actually we have a very poor selection of features for 1 pixel, because in particular we don't use any special information about neighbors. And usually when you want to segment an image, neighboring pixels should be in the same object. And here we will see how we can improve on the clustering we did before. So I will use the spices image that I just loaded as an NumPy array. And let's try to segment the different heaps of spices using the previous k-means approach that we used. And you'll see that the result is not really good. So the problem is actually that your eye is able to distinguish the different colors, but that we have a lot of texture coming from little shades that you have on the spices. And it takes some time to execute it, but it will come. So during the time it takes to execute the cell, I have a question for you, which is, if I wanted to enrich my selection of features for each pixel, which other kind of information could I use? Any idea? So we already have the RGB or LAB numbers, but what kind of other numbers can I get for one pixel? Transparency, if there were a transparency channel, yes.
You could calculate some sort of statistics over a window, so like you see the full curve.
Exactly. So that's one very important idea to enrich the selection of features is to use information about the neighbors. Exactly, and we will see that in the following part where we will use Gabor filters, which are texture analysis features. But here we will use a very simple information about pixels, which are their coordinates, XY coordinates. That's another kind of numerical information that we can use. And this will be done by this superpixel algorithm that we will use. But so you can see here that so that's a result of our segmentation, and it looks good, but I wanted to have uniform patches of similar color, and here I have a very fine-grained texture, so I was really not able to segment the different patches. And you can see here I use this very nice mark boundaries functions from the segmentation submodule of scikit-image to show the boundaries between the labeled, the segmented regions, and you can see that it's full of noise. So really not a usable segmentation that I could have. And therefore, we will use the slick superpixel algorithm, which segments an image into patches. And these patches are called superpixels of neighboring pixels with a similar color. And what's nice is that Slick is also a k-means clustering algorithm, but that uses both the color information in the LAB color space plus the XY spatial information, or XYZ spatial information if you're in 3D. It also works for 3D images. So we have more features, LAB, XY, and Slick just performs clustering in this multi-dimensional space. And you have a compactness parameter that is quite important because it controls the relative importance of the distance in image and color space. Because you see here that we're starting to mix together features that are not homogeneous. They don't correspond to the same physical quantity. For example, colors can be between 0 and 255, and XY coordinates, they can be as large as the number of pixels that you have in the image. So I need some way to normalize the distances between the different directions, and this is this compactness parameter. So this slick superpixel algorithm is found in the segmentation submodule. And I executed it on the spices image. I say that I want 200 segments with this compactness parameter that is close to the default value. And then I plot the resulting segmentation. So you see that the superpixel algorithm segments different patches that are quite compact, but that the boundaries of the patches lie quite well on the boundaries of the objects I want to segment. So this is quite nice. And after, I can so my segmentation is not finished yet, right? Because I have as many labels as patches. But I can create a posterized version of my initial spices image using the segmentation. So this will be my new image where the texture has been removed. And then I can add a second clustering step on this new image in order to have a smaller number of labels, which is what I do here. So this time I call explicitly the k-means algorithm. And it will take some time. And here I plot the boundaries. So you see that it's not perfect, but some of the objects have been well segmented, and it's much better than the initial segmentation, right? So remember that this slick algorithm, it's just a clustering algorithm, but that mixes together the color information and the spatial information about pixel coordinates. So I have a small exercise for you, which is to load the astronaut image, and then to repeat the same operation. So you might want to do a lot of copying and pasting of code, and do the superpixel segmentation followed by k-means clustering on the astronaut image, and to see if you can have a nice posterized version of the astronaut image. So depending on your version of scikit-image, this kind keyword argument here can be either mean or average. I think I'm running master, but yeah, but the documentation says average, so well, it should be the same, but sorry for the confusion. Okay, so in the solutions notebook, I just copied and pasted the code from the spices example for the astro array, and the exercise was to change the number of segments, which is the number of superpixels, and also the number of clusters. And so what's interesting, for example, is that if you put a small number of segments, then the solution is not very good, because you don't have enough patches to follow complex edges that you might have in your image. Whereas if you put a large number of segments, like I think I had 500, then, for example, the orange, what's the English for that? Coat or of the astronaut. The orange jacket is really well segmented, as the NASA logo is well segmented. So for superpixel segmentation, usually asking for a large number of superpixels is a good idea, because it already reduces the number of information a lot that you have in your image, and after you can always do other operations on the superpixels, because with superpixels you never obtain from the start the segmentation that you want. You need a second step. So it's better to have a large number of superpixels that will follow the edges of your image well, and after you do the second step that you need to.
Quick question.
Sure.
Is there some sort of ratio of the actual pixels to the number of superpixels that you usually stuck with as a guess, or?
So there is a default value in the slick algorithm. I don't remember which one it is. So it's a fixed number, so it doesn't use a special heuristic like what you mentioned, but segmentation.slick.
It sounds like
yeah.
you just have to play with it.
However, it will depend on the typical size of objects. If you have high resolution image with a lot of pixels per image, you don't need as many patches compared to the case where you have a lot of very small objects. So if you wanted to estimate automatically the best number of super pixels, I think I would do something based on edge detection and try to count the distance between edges or something like that, and then this would give me a typical scale. But it's really not guaranteed. Yeah, sure.
Another common approach is to over-segment the image, and then we've got region adjacency graphs. So you can set up a graph across your whole image, across all the superpixels, and then you merge the superpixels according to some rule. So that way you can start with the big over-segmentation and then just merge them into bigger superpixels until you're satisfied. There's an entire segmentation tutorial in the tutorials folder, the lectures folder.
Okay, let's move to the next part, where we will increase more the number of features. The more the better in terms of features. And the difference compared to the other sections will be that first we will use texture-based features, which are these Gabo filters. And also we will not do clustering, we will solve the classification problem, meaning that we will have a training set of pixels that will be labeled by the user, and the algorithm will learn the class of the non-labeled pixels. So for this example, I'm going to skim over it very briefly, just to explain to you what are Gabo filters. They are texture kernel with a sinusoid that decays with a Gaussian kernel, meaning that it's able to detect variations like edges, for example, or it can detect more complicated textures. And here, so I'm going very quickly over this, but you will have time to look at it later. And yeah, this was just the example to plot this Gabo filters here. And so here I define a function to compute this Gabo filter features out of an image, but for the sake of speed, let's consider it as a black box function. I have an image and it returns a vector of features for each pixel. And I will use a random forest classifier, which is another estimator from scikit-learn. So why do I use a random forest classifier, not one of this SVC support vector machine classifier? It's because here I want to use a very large number of features, and I don't know whether all the features are relevant or not. And for example, if I have a lot of very thin edges, some of the Gabo filters will have a lot of information, but the ones corresponding to low frequencies will not. And the random forest classifiers is able to decide which directions of space are the most relevant and which should be used more for the classification. So that's why we use this random forest estimator, and we use an image where we define a mask with some regions that are labeled by the user. So here I have a mask where the sea is labeled, some part of the vegetation too, and some part of the sand. And so this will take some time to execute. But you can see here in the function that this classifier has the same syntax, the same API with the fit and the predict method as the SVC classifier, so that once you know which estimator you want to use, you just need to use fit and predict, and that's it. Still running. And so the function trainable segmentation here, it uses the image that I want to segment and a mask of pixels that have already been labeled. So this mask here, it's just the array of which contours are represented here. It takes some time. That's the downside of using a large number of features, right? Because if I used only 3 features of color, then it's much faster. But here I have a large number of dimensions, and also the algorithm has to decide where to find the best threshold. So random forest is actually quite complex. But as you can see, the result is quite good. The C has been really well segmented, and it's actually a very powerful way of doing segmentation by just giving a few pixels that have the that belong to a class of pixels that we want to segment. So I don't know if you're convinced by this kind of algorithm, but what's really nice is that you don't have to extract yourself very specific features. You can just say, okay, let's take all Gabor filters, and the random forest classifier will decide which ones are the most important. Any question on this example? I don't know if some of you are using ImageJ or Elastic, for example. These are softwares that have plugins to perform this kind of trainable segmentation where you can brush over some parts of the image, and from this labeled pixel, the algorithm will use them as a training set and after use a random forest classification. So you can do this with scikit-image too, which is pretty cool. Okay, so I have, say, 15 minutes left. And I will go to quickly over 2 other examples. The first one is using mid-level features. So up to now, samples were pixels, and we had a number of features per pixel, either color or texture, spatial coordinates, and so on. Now we will have a different kind of features, which will be here, for example, corners. So in an image, it's possible to detect locations of points of interest, and it will be useful, for example, to be able to compare images together. And here I used this corner Harris function from the feature submodule of scikit-image, which detects the location of where you have a corner. And you can see that here, for example, it looks like a corner, here too, and so on. And this points of interest can be used to match together images where you have the same objects. So it can be used for object recognition or for image registration. And if you click here on this panorama stitching link, so I'll go very quickly through a small example where we want to do panorama stitching. So we have 2 images that were taken but at different heights, because our objective doesn't allow to have the whole monument in the same image. And we want to stitch them together. So how can we do this? We need several things. We need to match points of interest between the 2 images, and then to find the best geometrical transformation that will transform one set of points into the other one. So in order to detect these points of interest, we use here what's called the orb descriptor, so ORD for oriented fast and rotated brief. So these are descriptors that are both scale and rotation invariant, because say that you want to detect, for example, the edge of the window here in the different image, they don't have exactly the same scale. They were maybe slightly rotated. So you need descriptors of your image that are both rotation and scale invariant. And so this orb descriptor is a very fancy object that encodes a lot of information about a neighborhood centered on a pixel with, for example, histograms of gradients, but at different scales and at different angles, so that you're sure that it's both rotation and scale invariant. And when you do this on the two images, so it's a very busy picture, the dots here correspond to points of interest, and these directions correspond to matching between the two sets of descriptors. And you see that here there is a general direction which corresponds to the transformation between the two images, but that there are also a lot of outliers that correspond to false detection of matching between the descriptors. And in order to estimate the best transformation between the two images to stitch them together, then we can use, once again, this ransack estimator that Stefan introduced for the shape of the sun, and that will find the best projective transform between the two images, and that will not use the outliers but only the inliers. And you see that after all the outliers have been rejected and the set of descriptors in image 1 are perfectly matched in image 2. So after you can transform your image, you can stitch them together, but that's really the important part in image stitching, is to be able to to match points of interest in the two images. Okay? So I'm sorry, this was really fast. I will take now 10 minutes for my last example. So I'm going back to the machine learning notebook for the last part, which is clustering or classifying labeled objects. So we have seen that once you have an image of labels, so I should plot it one here. Say we have an image of labels here, and we will want to classify these particles into two groups. Say we have the compact ones and we have the elongated convoluted ones. So you can imagine that these blobs are the result of great segmentation that Claire did on her cells, but I'm not doing any segmentation here. I'm just using the data.binary blobs function of scikit-image that creates an binary array of blobs. So it's quite useful as a markup for tutorials. And after I define a image of labels, and remember that Claire introduced this measure.regionprops function for the labels, which can be used to compute the area, the perimeter, the solidity for every object, for every labeled object. So the solidity, it's a ratio between, so what's the solidity? I know I defined it here. Yeah, it's the area of fraction of the object as compared to its convex hull. So if it's really not convex, with a lot of convolutions, it will have a low solidity. And so we take the area, the ratio between squared perimeter and area, which will vary whether your object looks like a disk or not, and the solidity. And so there you go, you have an array of features. Each of this property is a feature, and each of the objects is a sample. So we can do machine learning, and in particular, we can do some classification. So, sorry, not classification, we want to do clustering, because we could, of course, click on some objects and use them as a training set for classification, but here I will be lazy. I will just do clustering, say, okay, algorithm, separate my objects into 2 groups. I want the compact ones and the elongated ones. And so it's quite easy. I create my k-means estimator, and I use this fit method that we already used with the array. So data, it's the array that I built using the properties. And after I use these labels that are returned by the k-means. And so here I just use some NumPy magic to reshape the labels so that it has the same shape as the initial image. But so when I do this, you can see that it's separated quite well some of the elongated particles, but I'm not very satisfied with the clustering. And in fact, what I've done was very silly, because I have used features that have very different orders of magnitude. Because the area, it can be a very large number of pixels, whereas the solidity will vary between 0 and 1. And therefore, since the k-means uses the Euclidean distance in this 3-dimensional space, the solidity will not count at all. I mean, the result will be the same whether I include this solidity feature or not. So therefore, before doing the clustering, what we should do is to normalize in some way the different features. And for this, you can either do it by hand, and this is what I do here when I divide the area feature, which is the first column, by its maximum value. So it's not bad, but first of all, dividing by the max is not very robust. If you have an outlier, then it will change a lot your normalization. And scikit-learn also provides very nice methods to scale your different features so that they all have the same variance and the same mean. And this is this standard scaler object from the preprocessing module of scikit-learn. And I would advise to use instead this standard scaler on your data so that it makes sure that all your data have this, all the features have the same importance. And as you can see, the long convoluted objects are starting to be better distinguished from the compact ones. However, in my properties, I included area, and here when I look closer at my image, I see that some objects are quite long and not compact, but they are small. Therefore, maybe it was not such a good idea to use the area property. So my final exercise for you will be to copy and paste this code and to replace the area property by the eccentricity, and to see if you get a clustering that is different from what we have done yet. And then you will be proficient with machine learning and image processing, and it will be Stefan's turn to finish and conclude. I will just show that the final clustering is quite good because even small objects like this that were not compact were clustered in the same group as a larger elongated object. So. All right, thank you very much.
Thank you. Right, so the last section for today is very short, and the reason is because I know very little about the topic. So the shorter I talk about it, the less the chance that you'll figure that out. So I'm going to just mention three things to you very briefly. The first is Keras, which is a library for describing neural networks. I'll show you how you can very rapidly execute operations inside of ND-image nowadays with a new feature inside of SciPy. And I'll quickly mention to you joblib, which is a library for doing batch processing. Well, it's not designed for batch processing of images, but it's very useful for that. So I think what we saw very recently is with sort of this third wave of neural networks coming through that, this romantic notion that we can basically figure out the best model to describe an image. Well, we have to throw that out the window, because it turns out that if you just throw enough computational power at the problem and you have a complex enough architecture, the machines are able to outperform us. They're able to label images better now than humans can themselves. There's been a particular success around image processing problems, so problems relating to detection of objects inside of images, labeling images with multiple objects, segmenting images, determining where those objects are, and just classifying images in general. So in that category of algorithms, neural networks have performed exceptionally well. A library that gives us easy access to neural networks in Python is Keras. It's a high-level API built on top of either TensorFlow or Theano. You can use either. And it can run either on your CPU or your GPU. I also want to mention that there's a very interesting talk coming up. It's on Friday at 2:30 p.m. By Daniil Pakhomov. It's fully convolutional networks for image segmentation. And why that's of particular interest is because many of these models are sort of limited to a specific input size for the image, but these fully convolutional networks can run on images of arbitrary sizes. So do check out that talk. Daniil happened also to be a previous Google Summer of Code student on scikit-image. So there are so many networks out there right now. If you look at this diagram, it exploded. There are tons of different configurations. In many ways, figuring out which network to use is not so much an academic problem, but an engineering problem. That bridge is being built, but I think at the moment, very much it's still sort of experimenting with different architectures and figuring out what works, and the why is slowly being filled in. But you may have heard of several of these, like the long-term, short-term memory modules that are used for analyzing text, for example, or the generative adversarial networks, where you have two networks sort of competing against one another. The one network is trying to generate an image. The other one is trying to figure out if the image it sees is generated or an actual image in the real world. So they're kind of trying to outsmart one another, and thereby both learning good representations of what's going on. Companies like Google have built these enormously complicated and massive networks. The diagram layout you see here is Google's Inception version 3. To train these things takes an enormous amount of energy, a lot of computation. It's not the kind of thing you're just going to do on your laptop in an afternoon. In this diagram at the top, these individual circles are nodes. But each layer over here is basically one of these blobs you see down here. So this is a massive network. But there is something you can do with these pre-trained networks. The networks themselves have learned fairly sophisticated representations of images. So even though they might have trained their image to recognize various objects like dogs and cats and monkeys and whatever, you can still use those underlying representations to your own kinds of classification tasks. And it's a type of transfer learning, I guess you can call it. And what you would do is you would take the network, you would slice off the last layers, and you would build your own layers on top of that and just retrain the last bit, freezing into place the features that have been learned by inception already. So there is an example of how to do that in the Keras repository. I give you a link to it right there. Keras also provides a scikit-learn compatible API, more or less. I can't say I've had great success using it, but it is there, and it's great. If you already know the scikit-learn API, you'll very quickly be able to get started with simple Keras models, at least. It doesn't support the entire scope of Keras, but for the simpler sequential models, in other words, linearly layered neural networks, you can use that API. So I'll just show you how the code looks in Keras, and what I'm going to do in this example is very simple. I'm going to generate a dummy data set, and it consists of 2 classes, 2 blobs, and I'm going to train a classifier to classify it. I'll first train a neural network. It's a very simple neural network. It just consists of a few standard layers. I haven't made any attempt to make a sophisticated network that does a good job, but this is a very easy data set, so it will perform well. And then I will use a random forest to do the same classification and just show you the comparison. And my hope is that you'll see that even on your laptop, you can start to experiment with these networks and see how they work. So yeah, we use some scikit-learn functionality to generate a test data set for us. The function we're using is called make classification. So just generate some dummy data for us, and then we split that data into a test set and a training set. So that basically just shuffles the data and extracts 10% of the data. We keep that aside so we can do testing. We train our models on the rest, and we verify the accuracy on the test set. So here's the definition of our neural network, where normally you start counting the layers of the neural network after the input. So a 4-layer neural network will not include it would be 4 layers on top of your input. So we've got a sequential network. The first is we've only got densely layered connections here. And the features that I generated are 2-dimensional, so it's just for each sample, I just have 2 values, so that's what I specify over there. In Keras, you only need to specify the input dimension of the first layer, because all the subsequent layers can infer that information from the previous layers. Then we add a dropout layer. Dropout basically randomly switches off inputs to a layer, which makes the network more robust to overfitting. So I do that. I add a few more layers like that, and finally, I just have a layer. Each layer has a nonlinearity that's crucial to neural networks. Otherwise, you would be able to combine all the layers into one linear operation. But the nonlinearities after each layer, that's very important. And the final layer has an activation, a sigmoid activation. So yeah, so we can compile this model. You'll notice here the model.fit, very similar to the scikit-learn API, and then we can evaluate it to see how we do on our data. So let's execute that. Let's see, it runs through a couple of training epochs and accuracy of 96%. Like I say, very simple data set. I can do the same with the random forest classifier. Create the random forest classifier, fit it to the data, score the data, and I get, almost the same accuracy out there. Let's visualize the results quickly. So there you see, this is the input data with real labels colored according to the actual labels. You can see 2 clouds with a little bit of overlap. And here are the very reasonable labels provided by the neural net and by the random forest. Now, we're interested in images here, so I thought it would be fun to just see how you can take a pre-existing network and feed an image into it. Many of these networks are now being published along with the research as Keras models. Inception, for example, is actually packaged inside of Keras. So do not execute this command unless you want to download 90 megabytes of data. It's a fairly big model. It might take a while. I've pre-downloaded it on my machine. So when you run this, it constructs the Inception version 3 network for you. And then you can start feeding images into it. So how do you do that? Well, like I said, many of these networks expect an image of a very specific dimension. In this case, Inception needs a 299 by 299 color image. So 299, 299 by 3. So we take our input image, whatever it is, we resize it using scikit-image's transform module, transform.resize the image to 299, 299, 3. We convert it to a floating point image, so it's now got values between 0 and 1. But Inception expects images to be between -1 and 1. So we just take that image that's between 0 and 1, we shift it downward, so it's between -0.5 and +0.5, and then we rescale it, so it goes from -1 to +1. And that we can feed directly into the network. So we ask the network to predict what is it that we see inside of our image, and to translate that into English labels for us. So let's see. I'm going to run the Inception prediction on Chelsea the cat. Let's see what comes out. Well, it says it's an Egyptian cat. That's probably true. Not a plastic bag. No. Let's try the cameraman. I don't think it was trained on humans, but it recognized the tripod. And let's try an espresso, image of an espresso. Boom. So that's kind of fun. So all those underlying representations that are contained inside of Inception, you can reuse for your own classification problem. Like I say, follow that link, you slice off the top layer, you add your own layer, and then you just retrain the last layer with your data. It's quite simple. There's a very interesting blog post that appeared recently. There was an episode in Silicon Valley where the developer built a device that would recognize hot dogs or not hot dogs. They built an app recently that does exactly that, and they've got a very good blog write-up on how they did that, and it actually teaches you quite a bit about neural networks and how to put them together. So I would recommend that.
You can download the app too.
Yeah, you can download the app. Does it work? Has anyone tried it? It works?
Totally works.
I only have not hot dog objects here, so I don't know if we can test, but...
If you just pull a hot dog picture
Uh-huh.
up on your computer and use it against that, it will work.
It works? Oh, that's awesome. I'm going to leave the technical detail of this section in the notebook for those of you who are really interested. But I do want to highlight it because it's a great feature of the latest version of SciPy that came out. SciPy has now made available this object called a low-level callable. And a low-level callable, before, if you wanted to run, say for example, NDImage has a generic filter object, a function. So you can call generic filter on your image. And what it does, it's got a sliding window that moves across your image. And at each position, it calls a Python function and puts takes the result and forms a new image. So at each window position, you have to execute that Python function, which is incredibly slow. But now with this low-level callable, you can write that function in C, and SciPy will call straight through to the C layer. So in SciPy's for loop, which is written in C, it will call straight through to your implementation. So it doesn't go through Python and gives you a huge speed improvement. So you can do this via two avenues at the moment. You can go either via Python, or you can go via number. How many people here use Python? And how many people use number? Okay, so for the 4 people in the room targeted with this exercise, I'll show you. Okay, here's the kernel. So this is the Python kernel. It's erosion that you saw earlier on for making binary objects smaller or gray level objects smaller. It basically slides a window across the image, and at each point it just contains the, it just calculates the minimum inside of that window. So there's the Python version of that. I'll also show you the number version of that, which is quite beautiful. So it's literally just for all the values inside of my window, calculate the minimum value and return it. And you have to decorate it with this function that Juan wrote. And that's a bit uglier, but you can hide that away in a corner somewhere and just call it like this. Anyway, you can get speed up improvements that put you sort of in line with ND-image, which was written in C, and now you can write Python code that performs at the same speed. And finally, I just want to mention to you 2 packages, joblib and this is now hard for me because I pronounce task, and you guys pronounce task, but dask sounds right and dask doesn't. So anyway, the package is called dask. It's dask and joblib. Dask is a fantastic package for distributing computation, for doing parallel computation across clusters or even just on a single machine. So take a look at that if you have a need to distribute your computations. Here I just want to show you joblib quickly. Joblib is included in scikit-learn and used for 3 purposes: to cache output of operations, so you don't have to run functions more than once. If you've run it with a specific set of parameters, it will not execute it. If you re-execute it with the same parameters, it will read the cached output from disk. And this includes NumPy arrays, which is quite handy. It does parallel computation as well to some extent, so you can do batch processing easily, and it helps you to log and trace your execution. So this simple example here, I import joblib's memory. I say, please cache things into /temp/joblib. And then I can create a cached version of any scikit-image operation, like let's say segmentation.slick. Here I define a cached version of that. So the first time I run that operation, well, here I just call it straight from the library, and it takes 2.66 seconds. Then the first time I called my cached version, it takes, oh, I ran this before, bad. Let's try that again. The first time you run it, you'll see it takes 2-something seconds, because it needs to compute the result and store it to disk. But any subsequent time you call it with the same parameters, it just loads it from disk, and it's blazingly fast. So this is quite handy if you've got a fairly sophisticated pipeline that you want to run and run over again and maybe modify a parameter fairly low down that pipeline. You can cache all the intermediate results. They will be reloaded, and then you can just recalculate the part that you actually care about. So yeah, so that's it from me. Thank you very much for your attention and for being here. I would love to see you guys at the sprints on Saturday and Sunday if you're around. If you have any questions using scikit-image, we love helping people to get their work done. So if you join us on the mailing list, we'd be happy to answer questions there. I tend to hang out on Stack Overflow quite a bit as well. Yeah, enjoy the rest of SciPy.